Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is timber arch structure design per the NDS 2018 in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Gerhard Riem will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Tiefenbach, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, we'll be taking a detailed look at the modeling loading per the ASCE 7 2016 and a full analysis of an arch timber structure in RFEM. Also be covering quite a few of these AutoCAD-like features during the modeling process. Then we'll get into the design of the members per the NDS standard, and we do have the latest 2018 implemented in our add-on module RF-TIMBER AWC. I'll further go into consideration of curved member design and how exactly the NDS addresses this. And finally, we'll touch on printout report options available within our program for our calculation and design results. So for those of you who are not familiar with our program, we do work with the add-on module concept. So RFEM is our main finite element analysis program. This allows us to fully model our structure. So all of our materials, our cross sections from the various standards are all available within this main program. We can even integrate with BIM software such as Revit, Tekla, AutoCAD. We can load our structure, set up our load combinations per the various standards, and we can run a full analysis. Now with this analysis, we're going to get information such as internal forces, deflection, support reactions, and we can take this information into our own design tools, whether that's spreadsheets, in-house programs, or other software if we'd like to do the design. But rather, we can also do the design directly within RFEM with the use of add-on modules. So we have this concept: only pay for the add-on modules that you need based on the type of projects that you're designing and materials and codes that are needed. So the first add-on module I want to mention in regards to timber design is RF-TIMBER AWC. So this will design our members per the NDS standard, and we have both the 2015 and 2018 for ASD and LRFD. And it's nothing more than just a simple dialog box that will pop up within our main program. In a similar fashion, we also have RF-TIMBER CSA. So today we won't be getting into this add-on module, but for some of the attendees that are joining us that primarily design per the Canadian standard 086, we do have this add-on module, and today's webinar will be extremely helpful because both modules look almost identical, so the same workflow can be followed. We also have RF laminate. So this is going to be for cross-laminated timber design. And we do have the NDS implemented there for both ASD and LRFD. We also can do a general stress design. This includes all of the manufacturers that we have for cross-laminated timber. And I did a previous webinar specific to this add-on module several months ago that you can find on our YouTube channel. We also have RF joints timber. So this is for timber member-to-member connection design with steel plates, including dowels, bolts, screws, nails. And we can design per the NDS standard here as well for both ASD and LRFD. And again, I have a previous webinar on our YouTube channel where I go more into detail on this add-on module for timber connection design. Okay, now we can launch the program RFEM. So when we create a new file, you can see here that we need to give it the program name or the model name here. And we are going to specify a three-dimensional model, and we want to design the load cases and combinations according to the ASCE 7 standard. Now, you can see that we have both the typical ASCE 7 2016. We also have this one specified as wood. So we'll be utilizing this today, and I'll show you the difference a little bit later on about why this is specific to wood for our load combinations. We also have the NBC standard here, as well as many other international standards. So once we are done with this, we can click OK, and we are immediately brought into our main program. So we have our graphical interface to work with here in the center. So as we begin to generate this model, we'll be able to see all of our input data available over here in our project navigator as well. So this will allow us to make quick changes to cross sections, to materials as this model begins to grow. Now we also have our tables to work with down at the bottom. So maybe perhaps you like to set up your model within Microsoft Excel. You can import in all that information. We can also export results after we run an analysis with this button here within the tables. And then up at the top, we have our quick tools. So we'll certainly be utilizing those today. So to begin with, I want to go ahead and expand my grid settings here. So I can right click under my grid to edit it. And instead of the default options of 50 feet on any side of the grid origin, we're going to change this to 100. Our model is quite bigger than this today, so this will just be helpful with modeling. So now you can see just my project grid here. What I can do is to change the work plane here according to the ZX plane. And we'll begin by drawing our first member. So I go up to my quick tools and I draw a new single member. This brings up my new member dialog box. The member type will be set to beam. This is just anything that's a typical beam or column. And we access our cross-section database. So here is where we're going to be able to find all of the various cross-sections from the standards, including the AISC, the CSA, the aluminum, ADM, and so on. But we have many other parametric sections as well. So all you need to do here is to specify your dimensions, and the program will calculate the cross-section properties automatically for us. So that's what we'll be utilizing today, is one of these parametric timber sections over on the right-hand side, and in particular a rectangular section. So for our glulam member, we want to specify 8 inches by 14 inches. Now we also specify the material directly in here. Now typically the default materials when you first launch a program are going to be steel and concrete. So we can always access our material database, and we can use our filters over on the left to filter to timber, to North America, and here you'll find both the AWC and the CSA. And furthermore, we filter to the NDS 2018, and we'll see pretty much every single material available from the NDS standard, which, as you can see, is a very long list. We can further filter to the available tables within the back of the NDS. So, for example, if we wanted to utilize glue laminated softwood timber, we can select Table 5A, and you can see our list is a little bit shorter here. Now, we can always take advantage of what's called a favorites group. When we activate our favorites group, or we make some edits to it, we can either add or take away additional materials that we utilize quite often for our projects. So we're not having to sift through these filters over on the left every time in that long list. So for example, I added my glulam material I'd like to utilize today. You can see all of the material properties are listed here. We can always add our own material here under this particular button. That will save it to our database, and then we can utilize that for any additional RFEM models. So once we've set that material, we click OK, and we click OK once more. Now, rather than drawing a straight member, which is my default option here, I'm going to choose this option in Arc. And what I will do is to first click on my drawing grid origin, and then a point way out here at 64 feet will be my second click. Now my third click is going to define the radius of this curved glulam. So I can either click graphically within the model, or I can just simply type in 40 feet on my keyboard. I hit enter, and now we have our curved glulam member. So with this member, I'm going to right click, and I'm going to create nodes on the line. And I'm going to add so many intermediate nodes. We will set this to 5. I click OK. So now all I've done is just add these intermediate nodes along the length of the member. I'm going to highlight everything here, including those nodes that I just generated, but take careful note, I'm not highlighting the two bottom nodes, and there is a specific reason for this. So I'm highlighting the member along with the nodes I just generated from right to left, and then we'll see everything selected, and I take advantage of my Move Copy tool. So I want to make 5 copies of this curved member, 16 feet in the Y direction. So with Move Copy, it's exactly as we'd think. But under these detail settings, what I can do is I can activate these options here to connect lines between the copied nodes. And even more so, I can assign a cross-section to those lines. So this is how I'm going to generate the purlins that connect these main rafter members. So I go in here to create a new template. And the member type here, I'm going to select as a truss member. So rather than a beam, I'm choosing the option truss. Now you'll notice that my member hinges are grayed out down at the bottom here. That's because we're assuming that you want a moment release, and we're only going to transfer shear and axial loads. So I access my cross-section library here to create my purlin member. We go back to the parametric section. And here is where I'm just going to type in 6 inches by 6 inches. I'm still going to utilize that material I've already defined within the model, but of course you can add in another material if you'd like here. So we make sure that we have this selected here, the 6 by 6. I click OK, and we click OK through these dialog boxes, back to our Move Copy, and looks like, sorry about that. It looks like some of these members here for my purlins didn't hold the 6 by 6 for whatever reason. If I double click them, highlight all of them just to edit, now we can select that 6 by 6. It's no problem. So to quickly make those changes here. Now, when I take a look at these smaller members that were generated, you'll notice that they're oriented in the vertical direction as we would expect. If we wanted to rotate these smaller purlins along the rotation of this curved glulam, we'd want to orient those and rotate them towards what's called a help node. So what I mean by this is if I go under my Views tab, and that would be here in my Project Navigator, I can select my members by a specific cross-section. And we will choose a rectangular 6 by 6. So now you can see everything else is grayed out within the model. I can't select it. And I'm going to activate here in my grid. I'm going to move my grid origin with this button up here in the toolbar to the top of my curved member. When I do this, I'm going to select a new node. What I can do is to simply click on a point at -40 feet from my grid origin, and I've just generated a node down here. So this is the centroid here, the center of our arc. Remember, we gave it a radius of 40 feet. So now I highlight all of my purlin members, I double click, and we can actually rotate these towards a help node. So I can graphically select this node I just created, and I want to orient the Z axis, which is the downward axis, towards this new node. Now when I zoom in here, you can see that these smaller members are now rotating with my larger curved glulam arch. Okay, so the next thing we would like to do is to add in some lateral X bracing here. And what I'm going to do for this is to draw a new member in a similar fashion that we just saw, but the member type here is going to be a tension-only member. So what this means is that if this member has any compression forces, it's going to be completely taken out of the model. But in a subsequent iteration, because RFEM is a nonlinear analysis program, if tension is reintroduced into the member, it will be reactivated. We access our cross-section database here, and I'm going to choose the round bar. For the round bar, I just specify the diameter of 0.625 inches, and I choose my material. Now, for my material, perhaps I have some type of cable or rod. We can filter to metal. We can choose one of the steel materials here. We also have cables where maybe you add in your own cable material. Now for today, we'll just utilize the steel A36 that I already had predefined here, and we'll go with that. Again, these member hinges are grayed out. Attention only member is going to have, of course, a moment release and really only take those axial forces. So I click OK, and I'm going to turn this into a wireframe view just so it's a little bit easier to snap to the various node points. And I start by drawing my first X bracing in this single bay here. I make my second X bracing, snapping to the various points, and you can see the program is detecting where these nodes occur and giving me the snap locations. So once I've done this on one side, I'm going to take advantage of our mirror tool. So I hold down my control key to select my first set of X bracing. I use my mirror tool, which is up here in my toolbar. We create a copy. We mirror it about the ZY plane. And then I just choose my mirroring point. So for this, I can graphically choose any point along the top of my member. I click OK, and now you can see those X braces were generated on the other side of our structure without having to manually draw them in. Okay, so the final thing to do for our members is to draw in some columns. So I'm going to turn back on my grid. I'm going to set the grid origin back to the beginning of my arch here. And I go to, once again, draw a new member. And the member type will be a beam. I access my cross-section database. And once again, the rectangular parametric section. And we'll choose a pretty slender member, 5 by 5. We'll utilize the same material. That's fine. I click OK. Now the member hinge, I want the member start to be fully fixed, but at the member end, I actually do want to release the moment. So we define a new member hinge at the member end, and you can see here our 6 degrees of freedom, 3 degrees in translation, 3 degrees in rotation. The program automatically assumes we'd like to release the moment, which we're doing so about the local Y and Z axes. Now we do have partial fixity here for spring constants. This would mean you don't have something fully fixed, not something fully released, but something in between. And finally, we do have nonlinear options. So if you'd like to define partial activity, maybe tearing, yielding, and so on, that's all possible. But of course, for our structure today, there's no need for that. So we just want a simple moment and release, and I click OK. So the first column is pretty easy. I can scroll down here to the bottom of my structure and snap up to that point at the crown. The other two, though, are a little bit more difficult to determine. So what I want to do is to snap at a point 16 feet over, but you'll notice the program can't detect here where exactly I'm crossing that curved glue lamp arch. So I'll just stop a little bit short there. That's no problem because I'm going to do so on the other side. And here I'm going to highlight these two members by holding down my control key. I double click, and actually, let me try that again. I right click, and under member, we have the option here to extend the member. And it's exactly as it sounds. We can extend the member J end to the next member or line. So the program will detect when it crosses that arch curve. I click OK, and now you can see the program automatically snaps those columns to that curved member. So I need to do the same thing on the rear side of my structure. So I hold down my control key to select those 3 columns. Now, a quick move copy approach here without going into that specific tool is to hold down my control key on my keyboard. I highlight the elements that I want to move, and I take advantage of what's called drag and drop. So by holding on to holding down the control key and moving that to a different location, it will make a copy, and now we can snap those columns to the back side of our structure as well. The other thing to notice is that the program did go ahead and break apart some of these members here, but other places it's not broken apart for these larger curved glue lambs. So I'm going to use this feature here, connect lines or members. And I'm going to highlight over everything on the right side of my structure other than my X braces. I'm also going to do the same thing on the left-hand side, avoiding those X braces. And let me make sure that I went ahead and did that correctly. And what you'll notice now is that I have broken apart all of these smaller segments. And you might be thinking, well, this doesn't seem very efficient because I actually want to design this as one continuous member. But in the program, we fully anticipate for this to happen. So we've created a feature called sets of members. So what I'm going to do is I'm going to activate here under my Views tab, my view of just my larger 8x14 members. So you can see only those main rafters are available here. I highlight all of them at once. I can right click, and under member, we have the ability to create sets of members. The program recognizes what are continuous members here with all of these smaller segments. I click OK, and now it's placed a very thin dotted line around all of these smaller segments to create what's called a set of members. So now we can utilize these sets of members for loading conditions and even design them as one continuous member. So now that we have defined our sets of members, the final thing to do before loading is, of course, to support the structure. So I'm going to go up here to define a new nodal support. We do have a few default options here, such as hinged or rigid. We can always create our own support definition. So again, this should look familiar, just like what we saw with the member end fixity. We have 3 degrees in translation, 3 degrees in rotation, partial fixity, and nonlinear options as well, such as sliding, friction. All of those are possible with these nonlinear drop-down boxes. Now for us today, we're just going to stick with a typical pin type application, which is the hinged. And what I'm going to do here is to turn this into an elevation view, highlight over the bottom of my nodes, and now you can see that pin support was applied to the bottom of all members at the base. So now we're finally ready to get into loading. So I'm going to create a new load case here up in my tool. And the first load case description will be dead. The action category is set to dead here. And the action category is important. This relates to the ASCE 7 load combination so that the program knows which load factors to apply to which load cases. So we'll leave this one as dead. You'll notice self-weight is automatically activated here for this particular case. So we'll leave that active. Now here is the difference of why we selected the ASCE 7 wood load combinations. We can set the load duration factor, or the load duration, which will apply a load duration factor later on in the add-on module for design per the NDS. Now this isn't totally necessary. It's just a helpful addition within the program. So even if you didn't have these options here, you were designing per some other standard, it's no problem. Later on, we can address the load duration factors. Now for our second load case, we are going to choose the option snow balanced. So I type that in, and the action category here will be set to snow. Again, self-weight is unchecked here. We don't want to count for it twice. The program is fairly smart, and it went ahead and defined a load duration of 2 months, but by all means you can adjust this if you see fit. And then we will make a copy of this one, and we'll call this one snow unbalanced. And the final load case here is going to be wind. So with the action category set to wind. Now the Actions tab here is for when we have multiple load cases under one action category, such as snow. We have both the balanced and unbalanced, so the program's asking us, do we want these to act together, to act alternatively, differently? You can imagine that for wind, we would have many more load cases when it comes to wind. So we'd want to make sure that we have those wind cases set appropriately for how we want them to act on our structure. The combination expressions, the program will generate both the LRFD load combinations and the ASD load combinations, but most importantly, under the load combinations tab, we can see those individually listed out here. So here are LRFD load combinations denoted by this orange color, and our ASD load combinations denoted by the red color. Finally, the results combination tab is going to give us our envelope solution for all of our LRFD load combinations, and then we have an envelope solution for our ASD load combinations. This is just going to show us back, once we do run an analysis, the maximum forces, maximum deflections, for example, of all these load combinations considered. So now that we have defined these different load cases and combinations, you can see them in our drop-down box, but we actually need to apply the loads to the structure. So I'll make sure I am under my dead load here, and the first thing I want to do is to apply an initial pre-stress to these tension-only members. It's going to give us a little bit more lateral stability under the applied loads. So those members are highlighted, and I go into a new member load. So we don't necessarily have to define a force here for a member load, but in this particular instance, we're going to define an initial pre-stress. Now the program automatically understands that this should be along the member's axial length, and for a tension load, this will be a positive 0.6 kips. And I click OK. So now we can graphically see that tension load applied to those X-brace members, and you can see here that I neglected to highlight these two members here. That's not a problem. We go back into the member load. The program remembers all of our settings from the last input, and then we can add in that additional load there. So we also want to apply some loads to our rafters here, and for this I'm going to reactivate only those curved glue lamps. So now everything else is grayed out within the model. I go to my new member load, and this time, instead of applying to members, we apply to sets of members. So remember, we generated those continuous sets of members, so we can also utilize them with loading. We change the load type to force in the global Z direction, and we apply a magnitude of negative 0.1 kips per foot. I click OK, and then I can highlight over my center arch glue lamps here. Now, as far as the two outer glue lamp members, I go back to my member load, and I just simply cut this magnitude in half because we don't have as high of a tributary area. So now this will apply 0.05 kips per feet. So that's all we need to do for our dead load case. Now, when it comes to snow loads, it's really not so simple, as we know according to the ASCE 7. The code calls for us to consider both balanced and unbalanced snow loading for curved roofs according to figure 7.4-2. And in our particular case today, we'll be looking at case 3, where the slope of our eaves are greater than 70%. So this little figure here shows us the loading that we should be applying to our curved roof based on these particular points here of our roof slope, including 70 degrees, 30 degrees. We need to know what our crown is, which is obviously the top of that curved glue lamp. So some geometry needs to be used here to determine these various points. In addition, we then take a look at the roof slope factor, C sub S, from figure 7.4-1. And finally, the missing entity here to determine the load is the ground snow load. Now, the ground snow load is found within our ASCE 7 maps, as we all know, within the standard. But I did want to point out something that we recently added to our website, and this is called the Geo Zone Tool. So it is available on our website at dlubal.com, and what we've done here is we've incorporated the ASCE 7 2016 maps, and we've synced them with the technology from Google Maps. So what you can do is just to easily type in the address of where your project is located, and we can determine information such as the snow load instantaneously. We also have wind loads and seismic loads. So to show you guys this, a quick example, I'm on our website now, which you can find it under Solutions, and you can see the wind and seismic zoning maps here. For my project today, I've typed in just, some arbitrary address here in Lexington, Kentucky, and I have my snow load turned on, and just like that, I have my ground snow load directly from the ASCE 7 maps as 15 pounds per square foot. So certainly test out this feature if you're not wanting to manually go through those maps within the standard. Now, we do give you a handful of clicks as a trial version, but if you're doing multiple clicks a day, you would want to consider purchasing a click request package from our web shop. So with that said, in the snow loads, it's really, again, not so easy because we have to determine what's the 70-degree point, the 30-degree point. So I created for my project today just a quick little spreadsheet here, and you can see along my curved arch member, I've determined what those various points are. I've typed in here my ground snow load of 15 PSF. Now with the equations directly from the standard, I've determined what these load magnitudes should be for both unbalanced and balanced loading. Now, the code allows us to have linear interpolation between these points. So I've simplified this spreadsheet here on my next page to just determine the various points along the member length and the snow load to be applied to it in kips per square feet. So I have this set here in my Excel file based on this particular case. I jump back to RFEM here, and we want to apply this balanced snow loading to our structure. So we go to a new member load, and I want to make sure I'm applying this as sets of members of force. We're going to apply it in the projected Z direction. So the code allows us to go ahead and apply this on the member in the projected direction, and we choose this option varying here. With the varying option, what I can do is at the click of a button, I can import in those loads along the X length of my member according to the ASCE 7 balanced snow. So now you can see them imported here. I click OK, and then what I can do is just to simply highlight those interior curved glue lamps to see that balanced snow load applied in the projected X direction. In a similar fashion for my two exterior curved glue lamps, I go back to my member load, I go back to my varying load case here, I jump back to Microsoft Excel, and I just simply change my active worksheet. So now I've cut those magnitudes in half to account for the tributary area. I simply import in, which a program will recognize what's the active worksheet. I click OK. And now I just snap to both of those exterior curved glue lamp members. The exact same scenario can be followed for our load case 3 for unbalanced loads. I go back to my new member load, and we select this varying load option. I jump back to Microsoft Excel for my unbalanced load case here, where I've set these various loads along the member length. And we import in from Microsoft Excel. I click OK, and then we can highlight these interior curved glue lamp members. And now we see the unbalanced snow loading on our structure. Now, you don't necessarily always have to import in from Microsoft Excel, of course. It's quite easy for our two exterior members here that under the varying load case, I can just manually cut this load in half. So I'll do that within the table and using my keyboard here. I click OK, and then once again, I'll just click on these two exterior curved glue lamp members, and we have all of our unbalanced snow loads applied. So as far as wind load, when we take a look at this according to the ASCE 7, we really want to follow the main wind force resisting system according to table 27.2-1. And this is a great table because it essentially lays out every step of the way of how we should apply these wind loads to our structure. Now, for the sake of time, I obviously won't be able to go through this in detail. I just want to point out a couple steps here that are relevant for our project today. The first is step number 5, where we do need to determine the velocity pressure. Well, this does require the basic wind speed, and this is where we can once again take advantage of that Geo Zone tool. So I jump back to our website here, and all I need to do is switch to wind at the top. And then automatically, I'm still looking at my same address. The maps will update according to the ASCE 7, and I can determine my basic wind speed is 100 miles per hour. And then I take this into my spreadsheets or whatever other tools I have to determine my various wind loads. The other step I want to point out is step number 6, where we need to determine the external pressure coefficient, C sub P. Well, for our arch roofs, we want to make sure that we refer to figure 27.3-3. So there is a specific procedure for arch roofs, especially when we compare that to all the different roof types here that we'd want to follow. So again, I didn't have time to go through all of this for our presentation today, but I just created a single case here for our wind load that will apply to our structure within Microsoft Excel. So in a very similar fashion, we go back to the member load, and you'll notice that I'm in load case number 4 here for my wind. I choose my varying option. I import in from Microsoft Excel so we can see how we have both suction and pressure along our member length. And we change this to the global X direction. I click OK, and for this particular scenario, I'll just highlight over all of my members, and now we can see that lateral load applied to each of our individual rafter members. So now our loading is complete, and we can actually take a look at the various load combinations to see all of those loads applied together. So we can see balanced snow loading, unbalanced snow loading, in addition to dead load, as well as wind load applied to the structure. And with that, we are finally ready to run our calculation. So remember, we're in our main program, RFEM here, just running the analysis. It is a nonlinear analysis taking into consideration P delta effects as well. So once this is done solving, we will see here our results, and we have a results tab within the project navigator now. So maybe I turn off my loads here, and the deflection's probably not so easy for you guys to see, but no problem. Under the display tab, we have our results tree here that's going to control how we're viewing everything graphically. So for example, I can change this to colored cross sections. I can smooth the color transition here so we get a much better view when we're looking at the various deflections for each load case and combination. So this just gives us a sense on if we accurately applied these wind loads, snow loads, and so on correctly to our structure, and how the deflection really looks. Now, in addition to deflections, of course, we're probably very interested in the member internal forces. So maybe perhaps I take a look at this single frame line here, and we create a visibility by selected objects, and I zoom in. Well, this is where we can take a look at our axial forces within our columns, for example, and our curved glue lamp. We can look at shear forces. We can look at bending moments in both the strong and weak axis direction, and so on. And we also have the ability to zoom in here for either members, or if I right click on my thin dotted line there, I can choose the option for my sets of members to view the results diagram. The results diagram is just going to give me a little bit more information along the member length about what's going on with my internal forces. So you can see I can activate these, and then I can scroll through along the entire member length to view these in more detail. We can even switch different load combinations here, and these will automatically update. We can print them off to our printout report, and many more options available here. We also have the ability to view our support reactions, so we can turn these on graphically here within the model. Now, all of this information is available within table format. Now we have our table for results views here that we can export to Microsoft Excel and to do our own design. So that is really a clear picture of what the analysis portion is all about. within the main program. So I'm going to turn off my loads here and my results, and we're going to make the clear distinction that I'm going to launch one of our add-on modules. So under the Data tab in the Project Navigator, you can see this long list of add-on modules. This is why we have the concept just pay for the materials or the standards that you use for your particular projects, because realistically, you're probably only going to use a small handful of these. So we can launch RF-TIMBER AWC directly from this list here. We also can access them from the drop-down box at the top where they're categorized a little bit nicer. Under Design for Timber, you'll see here both TIMBER AWC as well as the CSA module. So we launched TIMBER AWC, and when I say add-on module, nothing more than just this simple dialog box that pops up within our main program. All of our load combinations are brought in, our materials, our cross-sections, our internal forces. We don't have to redefine any of that information. But you'll notice now how I am going to define additional information specific to the NDS standard that we didn't do back in the main program. So the first case I want to design here, and I'm going to go to File, Rename Case, we're going to call this one Columns. And I'm going to graphically select here my 6 column members, and I can zoom in to highlight these, and the program will automatically select those numbers and it inputs them in here. We have designed per the ASCE and LRFD for both the 2018 and 2015 standards. We'll choose the LRFD 2018. Then for my ultimate limit state design, I can choose my LRFD load combinations, and for serviceability, I can choose my ASD load combinations. Then it's really just as easy as moving down this list. So again, my materials are brought in from the main program. Here's my applicable glulam material with all of my material properties listed. My cross sections are brought in. For this particular one, we're just utilizing our columns here. Load duration, remember back in RFEM, I said that we can set the load duration for each individual load case. So that's brought in. But it's not totally necessary because you can always adjust these values here. So you can see the load duration factor is automatically set. Under the standard button at the bottom, that's where you're going to see all of these different factors directly from the NDS. So these are brought in straight from the code, but we do give you the ability in some situations to adjust these if you see necessary. In-service conditions, is your timber dry? Is it wet? You can select that from these drop-down boxes, which will again adjust those factors accordingly. The effective length, so this is the stability checks for buckling about our strong axis, buckling about our weak axis, as well as lateral torsional buckling. Now the program is going to default to the full member length here, so you'd want to override that if you had any additional members framing in that we didn't model, which are bracing those in any which way. So we'll leave these all as the default settings here. Additional design parameters, again, just a few more options here to select down from the drop-down box, which will adjust those factors for our design. Serviceability data, this is where we want to select member from our drop-down. And if we are interested in the deflections of these members, we can go ahead and highlight all 6 of them again. We click OK, and you'll notice that the program defaults to the full member length here. We also can add in a pre-camber. So this is the information that's going to be used to compare the deflections from our analysis to the limiting deflection ratio. The limiting deflection ratio is available under the Details button here, and we go to the Serviceability tab, and here is the limiting deflection ratio, L over 360 for simply supported, L over 180 for cantilevers, but you can always adjust these as you see necessary. So we'll leave those as the default settings as well. And lastly, we have a cross-sectional area reduction. What we can do here, if we have any notches in the wood, we'd like that considered. You can go ahead and specify the geometry here as well as where that notch takes place along the member length. But for today, we don't have any of that applicable for our model. So we run the calculation. It solves within a split second because we already have those internal forces from the main program. All I'm doing is bringing them into this add-on module and applying the NDS equations to those particular internal forces, and the program will let me know if I'm either passing or failing. So we can view design by load case, design by cross-section, which we only have one cross-section for our columns, or design by member. Within these tables, what's nice is that as I scroll through them, everything's synced up in the background to RFEM. And that big red arrow is showing me exactly where the controlling internal force is for that particular check. So we can see all this information listed here. In addition to that, you're going to see all of those adjustment factors that we set at the beginning of the input data here, all listed along with any other code references that were applicable for this particular check within the NDS. We also have all of the variables listed here, and finally the design equations are given again with NDS code references, so certainly not a black box application. We're trying to give you as much information as possible so you understand exactly where this code check came from. So you can export all of this information directly to Microsoft Excel, and we also can view it graphically. So if we're interested in viewing the design ratio, we just click the graphics and we're back in RFM, but we're technically still within this add-on module, and I can see that from my drop-down box at the top. I'm just viewing my code checks for both ultimate or serviceability limit state graphically within the structure here. So just a nice visual representation. So that's really a quick application, of course, how we can just design these straight members. Now, what we're really interested in is the design of these curved glue lambs here. So what I'm going to do is to go back to my add-on module, and I go to File, New Case. And I can create a second description here called rafters. Now I can always jump back to my columns. I didn't lose any of that information. I'm just creating an additional case here so that if I want to design my rafters separately from the other column members. So what I'm going to do here is to clear out the selection box, and instead I'm going to design all of my sets of members. Remember, we only have 6 sets of members defined within our model, so those are listed here. Now, realistically, this is the exact same procedure that we just saw for our column design. We move our LRFD load combinations for our ultimate limit state, and we move over our ASD load combinations for serviceability. And again, we're just moving down this list here. Now, there are a few key differences now for curved members when we compare that to straight member design, which I'd like to point out. So materials, nothing new here. Cross sections, same concept. We're just bringing in those cross sections. Load duration. We have added a column here for loading condition for the radial stress design. So you'll want to check this, which I'll get into radial stress design in just a minute, but to make sure that this is set to the correct type of loading condition for our curved members. In-service condition, nothing new here. The effective lengths, we cannot check stability here of these curved members. It's just a complex situation, so unfortunately that's not available here to check buckling about strong, weak axis, or lateral torsional buckling. So that's why everything's grayed out. Now, additional design parameters, nothing new here, but we will see a brand new table called curved members. And what we have listed here are the thickness of our laminate layers, which is set to 1.5 inches, but you can of course override these. And you'll immediately see a check here of the thickness of that laminate layer over the radius of the member, and we're comparing it to some ratio here. Well, this ratio comes directly from the NDS standard, and I'll actually show you guys that in just a minute, but just know we are doing this check before you even run a calculation, and it will flag us if we're exceeding this ratio. We're also telling the program to run a radial stress design. Again, I'll touch on it in just a minute, but by checking this option, the program will go ahead and design that as well. For serviceability data, what we want to do here is we want to choose sets of members instead. Now I can either type in sets of members 1 through 6, or I can graphically select them within my graphics view here. It will default to the full member length, so we can see here 74.18, that's fine. Cross-section area reduction, nothing to do here, and we're ready to run this calculation. Again, solves within a quick second. We already have those internal forces, and we can immediately jump to the design by sets of members. So before I get into the details of this, I'm going to jump back to the PowerPoint to discuss the design of these curved glue lamp beams. Now, my colleague Gerhardt, who's our moderator today, did a great knowledge-based article available on our website that refers specifically to how the NDS handles the design of curved glue lamp members. And there are a few key points that I want to discuss here within our presentation today. So with these curved members, there are variable bending stresses throughout the beam depth. And this means that it's not a linear relationship, but rather non-linear. As we can see depicted by this figure over here, we look at the bending stress diagram throughout the depth. Well, this is due, first of all, to the geometric shape. It's a curved member. That's why we're first seeing these variable stresses, but also because of the manufacturing process. Stresses actually occurred during the bending of these laminate layers when the manufacturer is generating these curved elements. So that's another reason why we have these variable bending stresses. Now the grains on the inside are also shorter than the outside. So what this leads to is to larger inner edge stresses when we compare that to the outer edge stresses. So the question is, well, how do we design this for 1D member elements, and how do we compare that to a more realistic 2D surface element within the program? So within this article, it goes into detail with a simple example here, which is exactly applicable to our structure today in terms of the curved glue lamp design. So with our 1D member elements, they're just represented by a single center line. So in order to determine what the bending stress is, we'll just take our bending moment and we divide by the section modulus. And here we come up with the bending stress. Well, when we compare that to a 2D surface element, so what I mean by 2D surface element, it has dimensions in both X and Y directions. We still give it the same materials, the same thicknesses, everything else, but now we can view the bending stresses throughout the depth of the beam. Well, what we find are that these stresses for a 1D member are less than the true stresses from a 2D surface element. So there's some discrepancy between there. So how can we possibly design for the correct bending stresses here when we're using 1D member elements? Well, the code addresses this with what's called a curvature factor. So the curvature factor is denoted within the NDS as C sub C. Within table 5.3.1, we can see here the adjusted bending design value equation given, and this utilizes several adjustment factors, with one of them being the curvature factor at the end here. The curvature factor is calculated according to equation 5.3-3, and we can see that given equation here. So we will take into consideration this curvature factor within the add-on module RF-TIMBER AWC, and we will see this listed in our results here. So this is going to accurately account for the increase of that bending stress for 1D member elements. Now, there are some limitations within the NDS where we do need to limit the thickness of our laminate layer to the ratio or to the radius of our member as well, 1/100 for hardwoods and southern pine, 1/125 for other softwoods. So this was what I was telling you, that we'll actually check this ratio before we even run a calculation within the add-on module. So that's what those ratio checks were all about before we ran the calculation that I pointed out with our curved member. So both will be accounted for. Now, the other consideration is radial stress, which is F sub R, which is induced by bending moment of our curved members. Well, when we have an increase in the radius caused by a positive bending moment, which we can see in this first set of pictures up top, we will have an increase in the tensile stress perpendicular to the grain. And what this can eventually lead to, if they're too high, is cracking within our glulam member, which is of course never a good thing. In turn, if we have a decrease in the radius, which is caused by a negative bending moment, we can see by the series of pictures at the bottom, then we have an increase in our compression stress perpendicular to the grain. Again, if these stresses are too large, then they lead to cracking and the compression stress as well. So what we need to do is to account for these radial stresses by running a design. Now the problem is that radial stress cannot be detected with a 1D element. So we encounter the exact same problem that we saw with the curvature factor. So therefore we must consider it analytically from section 5.413 within the code. And what this tells us to do is to check both the tension and compression stresses with the given equation here. So you can see that we're utilizing the moment, the dimensions of the beam, the radius of the member, and we're going to make sure that they are less than or equal to the design radial tension value. And again, this is given to us within the standard. If we are exceeding this and this is a problem, it can lead to cracking. So we are going to do this check for the analytical approach from the NDS. Now, when we compare this again to a 2D surface within the program, and we use the exact same materials, but again, we use a surface with two dimensions in X and Y. What we find is that this radial stress is almost identical to the analytical procedure. So that's obviously a good sign that the NDS found a good approach to accurately account for this, and we can view that and compare that within RFEM by creating a 2D surface model and see it matches up quite well with our results from RF-TIMBER AWC. Okay, so going back to the RFEM model there, all I want to point out here is that if we look at our results by sets of members, we're viewing the strength and bending. We can expand the adjustment factors here, and here is our curvature factor that I mentioned, so referencing section 538 from the standard. We're also checking the radial tension perpendicular to the grain, again with all those code references given directly from the NDS standard listed here, and we'll also check radial compression perpendicular to the grain. So everything that we just covered in the PowerPoint is also addressed here for curved glulam members within this add-on module. Again, we can export this information to Microsoft Excel, and we can also view the code checks here graphically within the member. So this really sums up the design of our structure per the NDS. So we've covered both the analysis and the design now, and the last thing I want to touch on is just our printout report options. What I want to do is to jump back to our RFEM results. So this is our analysis results. Maybe I go back to my global deformations, I turn off my support reactions, and I'm interested in printing off maybe some various deflections here for different load cases. And under the display tab, I'm going to completely turn off the underlying model. So what I can do is just to turn on and off several options here at the top, but if I uncheck model, I'm only viewing the deflected shape for all of my various load combinations. So if I wanted to print off multiple load combination deflections, you might be thinking, okay, well, we'll snap a picture, add it to the printout report, change the load combination, snap another picture. But we have a very useful feature in the program called mass print. What I can do is to access this option up here to print my graphic, and you can see mass print available to us here. So I can go into the detail settings of this, and in particular the results tab, and the program assumes I probably want to print off what I'm currently looking at. So you can see here global deformations are listed, and I actually can choose this option here where I can move multiple load combinations for consideration of these pictures. I'm going to choose all of my ASD load combinations here, and I move them over to the right side. I click OK. So now I click OK through these dialog boxes. The program creates these pictures and it says, well, wait a minute, you don't have a printout report quite yet. So do you want to create one now? And we can choose one of these printout report templates by default. And so we'll just choose this first one. And what will happen is a completely separate application will open up for our printout report. And in particular, we just generated all of these various deformation pictures for our ASD load combinations. So we'll see them listed immediately here. The program jumps us to those particular deflections. So let me zoom in here. And we jump to one of the pictures and we can see the deformations for each of those ASD load combinations. So the program automatically created them. Now, if for any one of these pictures I really don't like the view, I want to make some minor tweaks, I can always right click to edit. It jumps me back into RFEM and let's say, okay, I want to actually turn this model around. Maybe I do want to activate my underlying model, my original model. I click back and what the program will do is it will update that particular picture according to the changes that I just made. So you can see it just takes just a second to populate and here is that new picture layout. What also is extremely useful is that all of these pictures will update if I make any changes to my model. If I take out members, I change cross sections, I increase or decrease loading, these pictures will update automatically so I don't have to worry about reprinting them again. So as far as our printout report navigator here, I'm going to go ahead and explain this in a little bit more detail. And what we can do is to collapse both of these options here just to make it a little bit simpler to see. We have RFEM, which will include our input data as well as our results, and we also have RF-TIMBER AWC. So when I expand the RFEM portion, we can see here all of our input data. And as I click on these particular options for these tables, it jumps me to that section within my printout report. Now, if for any reason I don't want to include any of these tables, I can always right click, for example, my lines, and I can remove them from the printout report. And the printout report will automatically adjust and repopulate itself. And now we have excluded that lines table. In a similar sense, if I have my cross sections available here and I say, well, I really want to move my cross sections next to my materials table, what I can do is to go ahead and highlight it over here in my project navigator and drag and drop it to a new location. And again, we get a populated printout report. The program will go ahead and adjust that as we've made those changes. Now, the results are also available to us here, so input data as well as the results. We can see everything listed within these tables. Under the Edit Selection tab, this is really going to control in much more detail what we're turning on and off within this printout report. This includes our results as well, so maybe we don't necessarily want to include all members, maybe we don't want to include all load cases and combinations. Everything you can control here with this selection. Now, once you have these options set, you certainly want to take advantage of saving these as a template file. So what you can do with a template file once you've turned on and off these settings is under Settings, Printout Report Template, New from Current Printout Report. So what we could do is just to give this one a name, whatever you'd like it to be, template. Now that template will be saved for any additional RFEM models within the future. So you don't have to go in every time and readjust and turn on and off selections, but save as many templates as you want. You can even add your company logo and information about the project and so on to these template files. Now, we also have access here to RF-TIMBER AWC. So this was our add-on module for design, which is all available to us within this printout report as well. We can view our input data from those various tables as well as design by member. We also have our second case here for our rafters where we can view design by sets of members. This is going to include all of the table design information with code references, which load combination is controlling in this table format here. Again, you can also add pictures in addition, which is a nice touch in addition to just the table views here. Okay, so that is just touching on our printout report. And with that said, we will conclude today's webinar. So you can always find more information on our website at dlubal.com. I always want to encourage everyone to follow us online on some of our social media sites. You heard me mention our YouTube channel has all of these previously recorded webinars as well as some short tutorial videos. You can find there. We also have the other social media sites which just keep you informed of events and conferences, different articles that we posted to our website and such. Our email at our Philadelphia office is info-us@dlubal.com. That's info-us@dlubal.com. Our phone number is 267-702-2815. So if you have any questions about today's presentation or anything else, feel free to reach out to us here. So we will have many more upcoming webinars. You can register at dlubal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these webinars will occur, so you can always register through there. Many of you are wanting PDH certificates for today. Those will be automatically emailed to all participants, so you don't need to request those. They will be emailed to you within the next day or two. And it will be available to the attendees who were here for the full presentation. So this is a stipulation required by the different states that were licensed to give PDH, that you are here for the full webinar. If there were additional attendees that did watch the webinar today that maybe didn't individually register, you will need to request your PDH by sending us an email to info-us@dlubal.com. So again, if you watched with a colleague who registered, but you yourself are not registered and you're wanting a PDH, please request this at the info-us@dlubal.com email. And with that said, I want to thank everyone for attending today. And as always, I hope to see you at our next webinar. Thank you.